Donc on va parler d'architecture et de biomimétisme. Alors, je ne sais pas si, petit sondage rapide à main.
Hi there, we'll be talking about architecture and biomimetism.
Bof, bof. Je connais un peu, j'en ai entendu parler. D'accord, je n'en ai jamais entendu parler. D'accord, merci beaucoup. Bon, on va faire une petite mise à niveau rapide. Alors, on organise cet échange, cette table ronde avec Rodolphe Debord de Rabot du Tilleul. Et il faut avouer que, Rodolphe, qu'on a un très beau plateau. On a un très beau plateau parce qu'on accueille Michael Pollan d'Exploration Architecture. Michael est vraiment
Hi, Michael.
un rare, très bon spécialiste de biomimétisme. On a beaucoup de chance de l'avoir et évidemment un excellent
Michael,
architecte.
can you hear me?
Un autre expert.
Michael is an excellent architect. Then we have Stephen Beckers. He is more an expert in circular economy than in biomimetism, but it has to do with living organism. And he is Stephen is a world-famous architect. And we have Jérôme Michaud-Larivière with us. He's going to show you this object because Renaud is a creator, and he's going to talk about micro windmills, so very trendy but very efficient innovations. So somebody from Belgium, from the UK, from France. So we'll let the South Hemisphere play rugby, and we'll be talking about biomimetism and architecture. So myself and Rodolphe. Rodolphe is Sustainable Development Director at Rabot du Tilleul. You're all familiar with Rabot du Tilleul, and as far as I'm concerned, I'm in charge of communication of something called CBIOS, which is a European Centre for Excellence and Biomimetism in Senlis. So let me start and ask a few words about what CBIOS is about. And I'll do that very fast. CBIOS is a response because we had a constraint and we try and turn a constraint into an opportunity. Senlis is 100 kilometers north of Paris, and we had an army quarter that was to be turned into something new. So we had two ideas. We wanted to develop businesses and research centers, and one scientist working with a large cosmetic company, you know, the one that you're worth it. And he said, we need to work on biomimetism. Bio what? Biomimetism. That's of great interest for industrial companies. It was marketed by Benius, and a biologist and an entrepreneur in the US, and it would be worth creating north of Paris to set up some kind of a cluster or a hub for this approach, which is speeding up for various reasons. So we could create this kind of a hub where companies, businesses, startups can work, and research centers can work together, because multidisciplinarity is of the essence. You know that nature is multidisciplinary by essence, and multidisciplinarity is very often a source for innovation. And very often entrepreneurs say, we are dying of working in silos. We need to meet people. We need a Japanese engineer to learn about kingfishers to redesign the Shinkansen, which is their fast train. We need to create opportunities for people to meet. So the idea is to federate, to bring together a community around biomimetism. So we have R&D, industrial centers. All this is very much scattered at the moment. So we need and set up this industry. We need to offer them a venue for them to meet. So the idea is very simple. And let me remind you that, well, of course, nature was present on this planet before man was born. It was born 4 billion years ago. And instead of seeing it as a source of constraint, we could look at it as a source of innovation and inspiration. One thing, Homo sapiens, which means the wise man, by the way, that's probably overstated, but Homo sapiens appeared 200,000 years ago. So if nature started the first day of a year, we, Homo sapiens, kicked in December. So nature started on January 1st. We kicked in on the 31st of December. I can't even show you because we kicked in on December 31st at 11 o'clock p.m. So we've been here for 11 minutes, roughly. So it's worth taking a look at everything that happened before us because nature is resilient and it's lean. It optimizes flows, energy, etc. So you've got lots of examples that you come across on a daily basis. And you know that, or maybe you've forgotten it, but one of the most traditional examples is that of Velcro. Georges de Mestral, in 1952, discovered that some flowers were stuck to his dog's hair. So it was dry glue, no formaldehyde, by the way. That's probably one of the major benefits. Winglets in planes are inspired from orcs. It reduces fuel consumption, 3.5% less for an A320. The Japanese fast train, the Shinkansen, had problems. It was making too much noise when it drove through tunnels. And the Kingfisher specialist came in. So they have kind of a funny nose on their high-speed train, but they save energy and they make less noise. Of course, we'll talk about surface and engineering with the Lotus effect, which is hydrophobic. So it's very helpful. I'm not going to give you all these examples, but Michael was talking about this blue ladybird. It's called the morpho. And by the way, it's not blue, but it's blue without pigments. It's blue because there's this surface lining. There are different strata that reflect the light in certain ways, and that inspired optimizing PC screens. Termites, world champions in air conditioning. Caro. And there are so many examples. Nature is a genuine source of inspiration. This is an abalone. Michael is going to tell us about abalone, not in the same way, but Canadians have built glass with micro-cracking, like in abalone, and made it 200 times more resistant, or 200 times stronger. So the idea in our cluster is to develop training, to organize conferences, to build companies for this ecosystem to work together and on the long run develop open innovation or cooperative research, which is crucial for certain companies. And I heard a scientist recently who said, when you know what you're looking for, you find what you knew already. So we need to ask different questions. And this is the idea we had behind setting up this research center. So many companies have joined us, like Renault, Air Liquide, Interface, L'Oreal, Eiffage. We have 3 competitiveness clusters, like Novtex for textile, IAR, agro-sourcing, UPTEX. So we have competitive clusters, industrial companies, and in sort of shaded gray, you have potential future members, they're part of research initiatives, etc. I'm almost finished in a couple of slides, but our objective is to try and contribute, to try and give life to this network that does exist. We have labs working with industry companies, but all the efforts are scattered. So the idea is to try and map all this expertise and take part in training programs. We started a year and a half ago. And on the long run, why not provide training for students, because we have lots of students looking for education in biomimetism. So one day this will emerge for sure. And we want to contribute and emerge innovative projects, and we want to educate political leaders. We try and educate them so that biomimetism is part of the future law. And of course, we want to develop this site in Senlis so that we have a larger number of companies joining us. And last but not least, this summer, well, you know, biomimetism is quite wide. So we started, we launched a working group on housing, because it's interesting to see how nature optimizes various flows. Michael is going to give us some examples of that, how nature optimizes interactions, recycling, local energy production, etc., etc. So this is the beginning of an initiative. This working group is going to work together for a couple of years, bringing together industrial companies and startups and research labs in order to map out the challenges in terms of energy consumption, flow of materials, etc. And maybe in a couple of years, we can start showing prototypes and more concrete actions. Thank you very much indeed. This was kind of a longish introduction, I'm afraid, but I wanted to give you some kind of background. So right now, let's listen to Michael Pollan and Stephen Beckers and Jérôme Michaud-Larivière, because they all have very interesting things that they want to share with us. And then we'll take 10 minutes at the end so that we can have a dialogue. Thank you. Michael, over to you.
Thank you for that introduction, and thank you for having me here. I'm sorry my French is really too terrible to speak in French, so you have to rely on the very good translators. And as Alain introduced there very effectively, biomimicry is based on a very refined source of solutions. The solutions that have been refined through an incredibly long and ruthless process of evolution. So as architects, there's a huge amount that we can learn from these, particularly in the field of biological structures. So for instance, this is the giant Amazon water lily, which has evolved to create these huge leaves that are nearly 3 meters across. And to keep that strong, it has this branching network of ribs. And we use that to develop a 3D printed table for our exhibition, which was in London earlier in the year. And this was developed using two forms of software. One was a software called SKO, which is based on the way that trees and bones grow. And then for the table surface, we developed an algorithm that was based on the giant Amazon water lily. And that produced an incredibly efficient solution. So this is using far less material. And this is where I think 3D printing is going to be a real breakthrough technology for biomimicry, because previously, complexity in manufacturing generally meant it was more costly. But now with 3D printing, there's actually no cost penalty for complex forms. In fact, there's a cost advantage, because if you put the material exactly where it needs to be, then you can end up using far less material, and then you save money. Here's another example of something that inspired a project that I was fortunate to be involved with. This is a marine microorganism called a radiolarian. And this was one of the sources of inspiration for the Eden project, which I believe is still one of the biggest greenhouses in the world. And we managed to design that in a way that was completely rethinking the building type of a greenhouse. Previously, greenhouses were nearly always made with glass. So here we were using a fairly new material called ETFE. and we had these spherical structures. And the most efficient way we learned from biology to enclose a spherical form is with hexagons and pentagons. And this is an example of a new car, the Daimler-Benz that's been developed using the boxfish. The boxfish has an exoskeleton. So they studied that, the engineers developing this car, and then they also used the software that I mentioned, the SKO software, to refine the design of that, to reduce the amount of material. And another example of biological structure, which Alain mentioned, abalone. I think shells were probably one of the first sources of inspiration for people interested in biomimicry. I think some of the first domes over churches and cathedrals were probably inspired by shells. But what we have now is much better scientific knowledge, so that we can actually learn more of the secrets that are found in nature. So the image on the right there, that's a highly magnified view of abalone, and is made up out of these plates of calcium carbonate, which are fixed together with a flexible protein mortar. And so at a chemical level, it's almost exactly the same as blackboard chalk, but because of this microstructure, it is 3,000 times as strong. And that means that you can build buildings using far less material. So we've developed a scheme. I hope this is going to work. For some reason, that's not playing. That's a shame. Is it possible to play that video? Okay, well, that's a shame. Maybe we could show that later on. That was a design for a house based on the same principles as the abalone. And it was using about half the amount of material of a conventional house. So now turning to branching systems in biology. Most branching systems in biology follow a mathematical principle that is known as Murray's law. And Murray's law governs the diameters of vessels in branching systems and also the angle at which those branch. And this appears to be an evolved minimum energy solution. And we use this idea to design a new concept for a data center. So this is inside a mountain in Norway that already has a lot of tunnels in it because of marble mining. And the advantage of this location is that the air is very cold. So all we had to do was to find a very efficient way of drawing this air through the individual blocks of the data center. And we used Murray's law to design that branching system. So that might look very biological, but it's not that way just because we like biological forms. It's that way because we identified the optimum solution, the perfect, theoretically perfect energy solution, and then we designed according to it. And we've played about with branching systems a bit more recently. So this is an algorithm we developed for a water treatment facility. So rather than laying it out in a very straight rectilinear way, we developed an algorithm that used Murray's law to determine the locations of the individual elements and also the branching. And if you look down at the bottom there, you can see that the total length of the pipework came down to just under 64%. And then we developed this a bit further. With this one, we decided to get much more realistic. So this was based on exactly the right elements of a water treatment facility. And also, we factored in the effective length of the pipework. So if you've got a straight pipe and you put a bend in it, that creates a certain amount of resistance, and it's possible to work out the effective length. And so this scheme, if you look at the total equivalent length, this came down really quite impressively. And one of the engineers before we started said, well, you're never going to improve on what the engineers have done. And they thought we were perhaps rather arrogant to assume that we could. Well, I don't think it was arrogant. It was just being curious. And we used examples from biology to develop a solution that was far more efficient. It would cost less to build, and it would use far less energy in operation. So I think we're going to see a lot more biological algorithms that will help us refine systems. This is another scheme we've worked on. This is a zero-waste textiles factory in India, where we use biomimicry to design a very efficient structure and also to rethink all the systems in the factory so that these became like a sort of ecosystem of interconnected elements. And there were three main realms. There was the factory machinery, there was the energy, and there was the water. And by getting the waste from one part of the system to become the input for something else, you can move towards being a very efficient, close to zero waste system. And finally, this is an office building that we developed using biomimicry, and we probably referred to nearly 100 different biological organisms in this scheme. And we ended up with a scheme that the engineers say will be one of the lowest energy office buildings in the world if it gets built. So what I hope you've seen is that you can use biomimicry to rethink almost any functional challenge. You can draw on that amazing source of solutions. And if any of you have any functional challenges that you're grappling with at the moment, then hold those for the question time and test me, and I'll see if I can come up with some biological organisms that you can look at. Thank you very much.
Merci beaucoup. Est-ce qu'on peut réessayer la vidéo sur la Abalone?
Can we actually try to sort of see that video again, please?
Bon, on essaiera de la montrer tout à l'heure.
Try to show it a bit later on, maybe.
Oh, yes. Voilà.
Ah, that's it.
So this was using the same approach as the abalone shell. So it was building up the roof out of very thin tiles that knit together to form a very efficient shell structure that should use about half the amount of material of a conventional house. Thank you for doing that.
Just one question. How do you get inspired? You are in a restaurant and you are eating abalone and you think, oh, that's nice. I could build a house like this, no?
Sometimes it works like that. So, yeah, sometimes you see something that works in nature and you think, I know what I can do with that. Sometimes it's the other way around. You identify the function first, and then you look to nature and you work with biologists to find out how that problem has been solved in biology, and then you translate that into architecture.
Bottom up or top down or
Yeah.
bottom up. Merci beaucoup, Michael.
Thank you.
On va tout de suite enchaîner avec... alors, je veux bien reprendre le diaporama.
We go back to the slides, maybe. Can you do this, or do I have to press something here?
Je suis à côté. Ah, ok. Hop. Yes. So Stephen
Beckers, if you'd like to show us what you've been doing, you're more into circular economy. So we have to be aware of the fact that each of these units, building houses, is part of an ecosystem, the urban ecosystem. You're also a specialist from an urban planning specialist. So you maybe it's not so much about those particular shells that you drew inspiration from, but do you see houses as trees or forests? Yes, thank you very much, Alain. So I'm not a specialist of biomimicry. I am inspired. I have been inspired as an architect by Cradle to Cradle, those of you who know that, which is called the circular economy in positive impact. And like most new models, which you can find this as a change of paradigm, it draws inspiration from nature. And the way I got to that project was that by having worked for a number of years, trying to reduce to its bare minimum the quantity of energy and materials that's used for erecting buildings. The first building that I drew a few years ago, which weren't built, and I'll only show you things that weren't built and others that are in the way of being built. But I'm not going to talk about architecture. I'm going to talk about the attitude that you have to have about projects. That's what we've been doing with various groups in France and with French architects. I'm a consultant. Lateral Thinking Factory draws from inspiration from cradle to cradle, circular economy. And we said it was important to have this interdisciplinarity in teams. So we have about 60 experts who are not in our company. There are just 7 people in Brussels who are spread out all over the world and are working in the most varied fields, from the technical to the philosophical, from the social to engineering, and which enables us to have a systemic look, a system-based look approach. So William McDonough is at the origin of this circular economy, which is the talk of basically the literature has been for the past 1 or 2 years, as you say, building like trees, cities like forests. It can look a bit naive at first. We made it with a number of projects. We're making progress. So what are we doing? So if buildings are like trees, they have to produce more pure water, nutriments and humus than they actually consume. That's what trees do naturally. They have to produce more diversity. So in our world, human world, it's a question of biodiversity, which is ours, social and cultural diversity, artistic diversity, or in terms of architecture. It's also producing more high-quality renewable energy than we consume. It's the positive impact of the tree, the buildings that we have to erect. So we'll see that trees produce biomass, and biomass can be energy for us. That's where the inspiration comes from. And also buildings must produce more healthy, upcycled material. It's every time we have to come back to the raw material. So in nature, this is done as a result of the biodegradability of materials, but it also goes as a result of the continuous upcycling in the technological sphere. So a tree produces more sort of oxygen than it produces. It does a lot of number of positive things. So we can see that buildings can do that as well. CO2 capture, the way we deal with it, is the production not only of biomass, but of nutriments or food, urban agriculture that capture the CO2 from the buildings as a result of human activity. And of course, behind that, there's high quality of life, flexibility. All this draws inspiration from nature, which has been evolving, and we tend to design buildings that are set, crystallized, with plans that we think are going to work for 50, 100 years. Sometimes they work. Very often, they have to evolve faster than they do. So why trees? As I said, trees captures solar energy, photosynthesis. It creates its own evaporation, which we can use in buildings and towns. So on a lower scale, we'll talk about that. That applies to towns, urban sort of islets, also in regions. The region, I would say, is a good unit to talk about the circular economy as we do. So the tree creates shade, it creates microclimate, it collects rainwater. You can see what we can do with buildings. It recycles wastewater. What the tree can do, the building can do. It can also produce feed. The tree is a metabolism, and we'll see that urban metabolism is an important element to reduce, not just by decreasing, but to ensure that towns are more resilient and autonomous. So I'll just give you a few examples. I won't be showing any architecture, but just talking about concepts. That is the concept of the building that we saw earlier on, where the trunk carries the energy, the waste, which become nutrients, if you're careful, that actually transport the energy throughout the building. You see on the right, the idea is to integrate to the buildings agricultural production, food, fish production. There has to be a continuous cycle in that to produce, as a result of all the nutriments that come from the building. You have a wind farm there on the left. I thought that the big wind farm was so ugly that I preferred Jérôme, so I used that particular picture. I liked it best. So we all know about solar panels and geothermic energy up to a certain depth, because one of the main elements of cradle to cradle and the circular economy is to base oneself on the energy that is provided by the sun. It's the only thing that comes from outside on this planet. So just a few elements now. We treat water biologically in those buildings. It's not very easy to do in France. To treat that and recycle it in buildings is possible in northern European countries, but not in France for health regions, health hygiene reasons. You can do that in Brussels, for example. There's a building that's 80% independent in terms of water consumption. It is occupied by the European Commission, 95% autonomous in terms of water, and the other 5% is also disposed of in terms of humus. We also treat rainwater, and it's the same thing for the urban agriculture. You sort of seize the CO2 of the building, you increase the performance of the buildings and produce nutriments, and it reduces the need for mobility in town.
So I'm not going to dwell much longer in this, talking about mimicry, but you see the parallel with the tree. The image maybe is a bit confusing of this tree, but when you treat every element, you have to do it in relationship with the other. Air, water, matter, they all have to be taken into account in a systemic cycle all together. And that's what is, it's like nature, because in nature you can't isolate elements from one another. There's no vertical isolation. You see on this chart here, diagram, you see we're talking about evolving buildings, city, neighborhood, and we can't say today how we will live in 50 years from now. I've recently worked on the specs for a hospital nearby, for the future hospital, in terms of circular economy. And what we've been able to understand with doctors and the whole management of the hospital is that they couldn't say in 2020 how surgery would happen with X-ray and so on. So we need to adapt buildings, and this roadmap is a way to improve buildings on a permanent basis. And so you need to be able to disassemble the buildings. On the right-hand side, in technological cycle, it means taking elements and using them, either metal or steel and others, or glass, and recover them in another building, or recover raw materials, commodities. That's the founding principle of cradle to cradle. On the right-hand side, you see woods, the cycle of wood that I've shown on the first building. On the first slides, I've shown materials that were biodegradable in our project. So it means that it doesn't mean that we take the wood and we dispose of it. It's using it in cascade. On the left-hand side, you see in several ways you can use wood, starting from the beam through its isolating insulation, compressed panels, paper, or in the end, and only at the end, you can burn it, and carbon goes back into the cycle to grow trees. And we do the same for water and energy. I'm not going to delve into these details, but with energy cycle, we know that when we burn gas at 1,200 degrees and we use water at 40 degrees in a house, you've wasted 90% of potential gas power. So all this is a mix of inspiration from nature, going into cascade, and doing the same with technology. There's a project with which we've worked with architects Olivier Jost and Carlos Arroyo, who's Spanish. We've worked on a house of project near Roubaix town, and it demonstrates how we can maximize biological and biodegradable matter in buildings, how we can optimize small technological elements to make sure they're upcyclable. And so this is a cradle-to-cradle project funded by C2 CBs, which is a European-funded program. To do all this, as in nature, you have to pool all your resources. Instead of a competition in architecture, we've invented co-petition, which means finding together solutions and defining a project together, and then everyone develops their projects based on a vision that was defined by all the stakeholders on a project. We do that for transportation. We see also on water and biological treatment of water, and also waste collection. Here, now, we've funded a company called Big Integrated Powerhouse. We have projects in Brussels, in Berlin, in Switzerland, in Bad Ragaz, and their greenhouse is integrating to buildings. Compared to what I've seen earlier, it's very simple. It's because we want to start with simple projects, but I'll go visit you, so that we can work together and give these greenhouses interesting developments. But today, energy production must be integrated into buildings. Thank you very much. Thank you. Thank you, Stephen. Just one question. Can you please give us an idea of the volume that it represents? Or to ask you maybe a bit slightly provoking question, are these projects still small, minor? Or can we have an idea now of the volume, the dynamics of these projects? And the second question, what are the obstacles that maybe are being overcome? Is it political, economic, cultural? We work at a very large scale. In Holland, in the Netherlands, we work with projects of 100,000 square meters based on cradle to cradle. In Paris, and projects here in this region as well with EDF utilities on projects that are really large projects. There is no cradle to cradle architecture or circular economy architecture. It's a way of doing architecture. Not everything is technological. I like nice-looking, good-looking architecture and technology. There are projects in Germany, Denmark, Norway, Belgium, in housing, hospitals, retail. Retail is really fastly evolving. You need also headquarters of companies. A lot of architects work in Sweden on huge projects inspired by biomimicry and this idea of circular economy. The obstacles now, they're mostly economic, as I said earlier, or maybe at lunch. If there is no business model that works with still at Rio 92 and no progress can be made, sustainable development in a way is a bit obsolete because it's about doing less harm. For us, it's more than this. It's all the innovations that we have. We guarantee a return on investment over the next, in 10 years. For some, it's long term. For others, it's not so much. But you need a solid business model. Otherwise, the system won't work. I've refused subsidies for some projects because subsidies is good, but when it stops, it all collapses. Subsidies in the beginning to help fund research, okay, that's fine, but not, then in the operation of the buildings in the neighborhood. But of course, if there's money here from people in the room, I'll take it. But you still need a strong business model. And for the rest, for 5 years, I've only worked on this field, and in the beginning, I used to explain what we did, and now we do it. Thank you, Stephen. Now we're very lucky to have Jérôme Michaud-Larivière. Maybe you know his product more than himself. Maybe some of you have heard about him because you're very famous in the media. So we're going to talk about trees. I won't say more, but I want you to tell us about BioWind. Oh, New Wind, sorry, is your project. You come from the movie industry, you were a scriptwriter. So how did you create this project? Tell us about the story of the tree, New Wind and the wind tree. I come from somewhere, and I didn't know where we were all going. And at the age of 50, I thought, well, I could do something very useful. But it's a citizen-based approach. After Fukushima, 2011, it seemed It seems that I had to find solutions at my modest level in terms of energy, and I wanted to provide the people with the possibility to create their own energy. And I had to find an easy idea that could be easily implemented quickly, something convenient, and that would be more than electrons, maybe emotions, that was ambitious. But it was really about betting on emotions. And so in terms of producing electricity, there were other dimensions. We were talking, it's about a whole continent not having access to energy. In Africa, a vast majority of people don't have access to electricity, so bringing few electrons to provide people with light, it can save lives. So imagine an easy solution that would be easy to roll out and that could save lives. It gives meaning to your life, and that was my motivation. And in urban center, 75% of the world population will live in urban centers by 2050 with huge needs in terms of energy. So you need to bring power generation closer to consumers and forget about outdated power plants that are very far from urban cities with huge losses in terms of energy. So for all different kinds of energies, both thermal, wind, solar. So bringing energy in the heart of the city with the wind, that was my idea. And that's what you came up with, yes. So the idea was to bet on residual depleted sources in urban areas. And instead of using something that existed and transposing that into the city as was used and it failed, we studied disturbance. And it's more biomorphic rather than based on biomimicry. We don't do photosynthesis with our solution, but in a certain volume, we can put micro wind farms, depending. So here, this is the wind tree. And you will see in the next slide, the tree is rotating. It's very peaceful. You see the branches of the real trees. They don't move. There's no wind. A very light wind is enough to make all the leaves move. There's a micro generator in each branch. It was about hiding technology in a natural shape. There are a number of micro turbines, and sometimes because of negative pressure fields, they can have a bad influence on one another. So because we looked at trees, we were able to put the micro turbines correctly, because branches divide in two to catch the light. And so for wind, for air, it's a bit the same. In order to make sure that all our trees, all our leaves would receive the wind, we positioned them like leaves on a real tree. The tree is very inspiring because in the developments, it's not really mature as a project today, but we treated the branches like bark and with silicate walls. And so there's a supplement of energy with light, and there's a whole structure bearing the leaves. Can you please comment on the performance of the tree? We see 4.1 kilowatts on this tree. That's the first solution that we're experiencing these days. In Düsseldorf, the first tree is being planted, and there will be more during the COP21 conference in the first 2 weeks of December. So these will be the first trees planted in France. So this is the pre-serial program. A lot of people have trusted us from the beginning of our project. But beyond the wind tree, we're developing other solutions that are less expensive so that everybody can embrace this. So there will be different shapes, and they will bring 2 to 2.5 kilowatt per hour. This tree is 4.1 kilowatt of installed power. So that's for a family. So you have the equivalent here. 83% of the needs of a 4-people family for a house of 55 square meters. So it's really about producing electricity at a micro level, at a very local level. Yes. There are 6,300 watts available at a given time. And it also depends on your exposure. When you're near the sea, it's more interesting economically speaking. What about the design? Does it participate to the success of your project? Yes. It's again because we're talking about biomimicry. It was, about emotions. In the beginning, I drew the trees and nothing would happen. I drew a tree with branches. And after 1 year drawing sketches, we couldn't find anything really that suited us. And then, you see there are 3 large trunks which favor performance and which are more airy. Thank you very much. That was very interesting. So we have 10 minutes. Now, I'm sure for Michael Pollan, Stephen Beckers, or Mr. Larivière, you have questions for them. So now it's your turn. Maybe you're wondering why I'm here.
Bon, pendant que Rodolphe fait un petit commentaire, on vous passe le
So,
micro.
Rodolphe will add a comment. Yes, in 2 words, I'd just like to say that I was very delighted to invite these eminent speakers on these subjects. I'm in charge of sustainable development at Rabot du Tilleul. We have a very pragmatic approach of sustainable development, and I see that 2 conceptual subjects were chosen. One, the economy of functionality. We're not going to talk about that today, and the other one is biomimicry. Biomimicry is a pragmatic dream. It's a dream because it's very inspiring. Every time we give examples to people, everybody listens. We see abalones. So people dream. And then when we go a bit further, every time we say less material, more performance, more this, more function. So economically speaking, it's very interesting. In general, you know, then there's construction gets involved, and there are regulations maybe that you want to put down, and then you have to convince investors that, yes, the wind tree, can't even call that a wind turbine, it will work, it already exists, and you can implement that in your project. So we don't work with Michael Pollan yet and with Michel yet, but we're already working, and we've worked with Stephen Beckers for a while. The nicest project in Lille region is Cradle to Cradle, and we're talking with New Wind to implement the first wind trees. Unfortunately, we're one of the only regions in the Lille region where there is no tree, and so he refused to put his wind trees in our headquarters, but there are other areas where we're based where his wind trees can be put. So it's also very pragmatic. Biomimicry, some say that it's about the how of sustainable development. 1 or 2 questions. I have 2 questions. One question for Mr. Larivière about is a tree. One is 10 meters high, the other one is smaller. It's been designed for individuals. Can you give us your prices? No, unfortunately, I can't. But of course, we'll have to provide people with an answer. We're working with people who manufacture these trees to give the prices. Of course, it provides a return on investment after 10 years. And we're trying to make progress in order to put this deadline to 8 years. And there are deadlines that we need to improve. For the bush, for the smallest element, it's about 8 years for the return on investment. And I can't provide you the price because we're currently working on this. And this probably be 6 years for the return on investment, and I think that's reasonable. There may be industrial partners or local authorities which will experiment all this, and maybe the price will be more stable when you start manufacturing it in series. Yes, and of course, in France, you also have the utility price, which is that of EDF, and so there are hidden costs, and our manufacturing, our production costs are transparent. We have nothing to hide. So we shall meet for the COP21 in November, and the prices then will be disclosed. Concerning regulations now, in terms of architecture, are there regulations? We're talking about obstacles earlier. For you, Is regulation today an obstacle? We're talking about tunnels and chimneys, also safety and health regulations. Is it an obstacle today? Are things moving when it comes to legislation? It's not an obstacle per se. Our small power units and our products, so we have to comply with regulations concerning wind, for instance, but there is no construction permit per se to install these trees. Stephen, a few words on regulations? Yes, we always have to face regulations and deal with them. In Paris now, given COP21, people tell us that we need to develop urban greenhouses, and regulation is evolving in the urban plan, for instance, so we can put things on roofs. But there's also regulations, so it's difficult to deal with because there are regulations on the number of floors of buildings, and it's like water, you know, you always have to insist. If there are limitations, regulations for wind farms, there are also regulations in other fields, so for PV, you know, there are regulations. It used to be the same for TV antennas on top of buildings in the past. We have to work with people like Jérôme and designers like Michael and find projects. And Rodolphe, by the way, thank you for gathering us all together here so we can continue our exchange in the future. But today there is an impetus. We're talking about circular economy, about the third industrial revolution in the region, and the strength that the power that the mayor of Paris has, or other politicians, to facilitate our work. So if we have good-looking, profitable solutions that meet the needs in terms of preserving resources and environmental challenges, I think doors can open, and very quickly. Another question?
Ah oui, allez-y, oui.
Bonjour, Nicolas Malaquin.
Hi, Nicolas Malaquin. I'm Flax Composite. I'm running a startup company, and I'm working in the textile cluster. And my question is to Michael, because I'm working on a composite material with flax. And this is a material which can be shaped thermally, and it's insulating material, good soundproofing properties. So how can I use biomimicry in order to improve acoustics in buildings? What kind of inspiration could I find in nature?
Did you get everything, Michael?
I can repeat in English.
No, that's fine. I got that. That's fine. Yeah, acoustics is quite a tricky one. There are certain cockroaches that are amazing at acoustics. There's a cockroach that builds a special burrow that is able to project its sound over a vast distance. But I think what you're talking about is a slightly different approach. I can't think of any particularly good examples of acoustic absorption in biology. But one thing that I think would be very interesting in the field of acoustics is something that is adaptable. You know, nature adapts and responds, and that's often one of the big differences between nature and man-made materials. So, for instance, in a lot of environments, in a restaurant, in an auditorium, you often have very different acoustic demands. You know, sometimes if there's not many people in here, it has a very different acoustic quality, but if it fills up with people, it's completely different. And similarly, in a restaurant, it starts off very quiet, but when it gets full, you sometimes can't hear anyone on the other side of the table. And what you really want, I think, is surfaces that can respond to that. And as the noise levels get higher, they start to absorb more sound. Orientation might be part of that.
Pour prolonger la discussion, je pense. On se dépêche de prendre encore une ou deux questions.
We'll take a couple of last questions. There is a website called Ask Nature. I don't know if you are familiar. It's asknature.org. I think. And maybe you'll find something about acoustic absorption. It's biomimicry 3.8. Hi. I'm a scientist and a researcher working in a school of engineering school, and I have questions about designing. In research, we see that there are lots of discipline involved, and I'm thinking about designing with engineers. How should we train our students to include multidisciplinarity? I'm really amazed to see people from different backgrounds working together on very complex models with lots of emotion. There is a mix of skills here, which is very interesting. So can you help me? Well, in a couple of words, I work with Brussels University, and I ask my students to work in teams. So I teach to engineering architects. That's already kind of an interesting combination. But we also try and find other students in other universities, and we get them to work together. We're trying to do the same thing in Addis Ababa with the University of Addis Ababa. And trust me, it works because they're willing to work that way. And professors are interested because they're fed up repeating the same thing they've been repeating for 20 years. So it's very interesting to get them working together. And each time I go to a meeting, someone is going to tell me about chemistry. I'm not a good chemist, so it's a challenge to me, but it's also very interesting. So it's this positive competition that stems from working together. You can't teach all subjects at the same time, but if you get people working in the field of finance, working with engineers, architects. As an architect, I never learned anything about finance, except for, balancing my checkbook. So it's important we can include these disciplines like we do. We have 60 different disciplines we work with, and we would call on one of our experts one every 10 years because he's a specialist in artificial coral reefs, for instance. So we don't call on him very often, but we did once. What's important is to identify people, and internet is great for that. So you can identify people who are very smart in their field of expertise and who can share. And this is what students should learn, how they can share their expertise. And if I may add one thing, in construction, as constructors, as builders, when we have a true project with a plot of land and we want to build this beautiful building, this is when we can start putting our head together with that of other partners to work on that type of project. Now, the question is, what's the optimal number of partners coming from other backgrounds, and do they get on well together so that they can work? When you have too many people, you can't succeed. When you have too few people, you can't succeed. But when you're thinking about a building with 80 housing units, I mean, that's a good project so that you can make good progress. Of course, you will have obstacles to overcome, but that's a way to move forward. And biomimicry and the poetry that biomimicking brings along allows us to think about innovation more. Michael.
I completely agree that it's really important to get people to collaborate. And often architects and engineers are not particularly good at that. Architects often, particularly the ones at the sort of iconic end of the spectrum, they like to do the sexy sketch, and then they expect the rest of the team to just make it happen. And I think that's almost insulting as a way of working. And when I'm putting teams together, I always try to bring together teams of polymaths, people who understand the other disciplines and can talk together and have a creative conversation, because nearly always the most interesting things happen at the intersection between different disciplines.
Oui.
I just wanted to quote Bachelard, a philosopher, who said that between research and knowledge there is an epistemological obstacle. And to overcome this, he offers effective and intellectual catharsis. He says we should refute any final and authoritative argument and to remain concerned. So Bachelard, that's kind of a reference. But in our area, the universities try and work on that, and they try and organize sharing and exchanges between the different academia. I have a question for the audience. How many architects are students in architecture in the room? Because I'd like to launch a core for project for biomimicry housing in Lille. So if you're interested, come and talk to me at the end, so that we can start and move forward. And of course, you've understood, these won't be monodiscipline type of teams. We need lots of expertise on the team. Hi, I'm Benoît Bourret from the Catholic University in Lille. We talked about being inspired from living materials, from animals, from biology. And my question is, well, for me, biology is a set of interactions as well between species with competing strategies, but also cooperation strategies. Sometimes some of them are cheating a bit, by the way. But would biomimicry have anything to tell to organizations, to ecosystems, human ecosystems, for which we're trying to increase new models that would be an invitation for people to cooperate, to work together? Can we learn anything from nature to design new operating strategies for companies? Michael, maybe, because there are implications in social science. So you're the expert, Michael.
Well, I think you were touching on two things there. It's partly about human behavior and partly about functional systems. So in terms of functional systems, like industrial systems, cities, buildings, there's a huge amount that we can learn from studying ecosystems and the way that ecosystems are generally quite complex, interdependent, interconnected, zero waste, running on current solar income. They're regenerative rather than extractive, and so on. So definitely there's a lot you can learn from that. In terms of the more sort of social side of things, there are interesting bits of research there. So for instance, on the office building that I showed at the end of my presentation, we studied a thing called Dunbar's number. Dunbar is a scientist, and he's studied optimum group sizes in primates. And he's concluded that an optimum group size is about 150. When you get above that, the number of different interconnections becomes too difficult for people to understand what everyone else in that group does. And then if you're interested in organizational change, there is an interesting guy called Paul Z. Jackson who has applied biomimicry to change in business. So I recommend looking him up.
La question que vous avez posée pour la ville, c'est exactement la question que j'ai posée au groupe de travail sur l'habitat biomimétique, qui donc dans la prochaine séance aura lieu le 5 novembre. Voilà, le 5 novembre.
Mimicking housing. How can I design a biomimicking house? That's of interest, but what's even more interesting is how we can renovate cities using biomimicry. I'm quite confident we'll find interesting solutions. I don't know what this will look like, though. Well, thank you. Thank you to our 4 speakers. Thank you very much, gentlemen.
Let's do it.
And let's do it.